Have you ever wondered how we measure the mass of enormous galaxies? It's a colossal task indeed. You see, astronomers rely on the principles of gravity and the speed of orbiting objects to calculate the mass of galaxies. This involves observing how fast stars or gas clouds rotate around the galaxy's center. The faster they move, the more mass there must be inside their orbits. Now you might ask, how do we observe these far-off galaxies? The answer lies in our advanced telescopes that not only allow us to see these galaxies but also measure the speed of these orbiting objects. And let's not forget about dark matter. This invisible yet influential substance makes up about 85% of a galaxy's mass. So, when astronomers calculate the mass of galaxies, they also take into account the gravitational effects of dark matter. So the mass of galaxies is not just a wild guess, but a result of careful observation and calculation. What makes a planet a dwarf planet, you might ask? Well, it's all about the criteria. A dwarf planet, unlike its larger counterparts, doesn't have the gravitational might to clear its orbit of other debris. Yet, it still orbits the sun and maintains a near-round shape, just like the planets we're familiar with. Let's talk about Pluto, the most famous dwarf planet. Once considered the 9th planet in our solar system, Pluto was reclassified as a dwarf planet in 2006. This icy body, located in the far reaches of our solar system, reminds us that size isn't everything. There are other fascinating dwarf planets too, like Eris, Haumea, and Makemake, each with its own unique characteristics. These celestial bodies, though smaller than planets, are no less important. They offer valuable insights into the formation and evolution of our solar system. Dwarf planets, though smaller, still hold a significant place in our solar system. How can we study the interior of planets without digging into them? Quite an intriguing question, isn't it? Well, it's not as impossible as it sounds. We've got some pretty clever techniques up our sleeves. Let's start with seismic waves. These are vibrations that travel through a planet's interior, revealing information about the layers beneath the surface. When an earthquake or a similar event occurs, it sends out these waves that are then detected and analyzed by seismometers. Next, we have magnetic fields. By studying a planet's magnetic field, we can gain insights into the composition and motion of its core. And then there's gravitational pull. This is a bit like a cosmic weighing scale. The way a planet tugs on a spacecraft can tell us a lot about its mass distribution, hinting at what's inside. So, there you have it. Even without physically going inside, we can uncover the inner secrets of planets. Ever heard of the cosmic web? It's not your average spider's web, but an intricate network that forms the large-scale structure of the universe. Laid out in a fascinating pattern of nodes connected by filaments, the cosmic web is a vast matrix of galaxies interspersed with enormous voids. But why is it significant? Well, the cosmic web is our cosmic roadmap. It helps us understand how galaxies, including our own Milky Way, are distributed in the universe. It's also a key to unlocking the mystery of dark matter. This unseen and yet-to-be-detected substance doesn't emit, reflect, or even absorb light, making it invisible. Yet we know it exists because of its gravitational influence on galaxies. Scientists believe that dark matter forms an invisible scaffold upon which the cosmic web is built. In essence, the cosmic web is not just a network of galaxies, but a treasure trove of information, a guide to unlocking the mysteries of our universe. The cosmic web, a vast network of interconnected galaxies, is the backbone of the universe. What role do magnetic fields play in our understanding of planets? Magnetic fields, a fascinating aspect of planetary science, are invisible forces that surround many celestial bodies, including our very own Earth. Studying these fields is like decoding a planetary shield, a shield that protects the planet from the relentless solar wind. Scientists use magnetometers aboard spacecrafts to measure these fields, giving us insights into the planet's internal dynamics. For instance, Earth's magnetic field, the geomagnetic field, is generated by the churning of molten iron within its outer core, a dynamic process known as a dynamo. But these magnetic fields aren't just for show. They are the unsung heroes of planetary life. They deflect the solar wind, those charged particles that the sun hurls into space. Without this protective shield, the solar wind could strip away a planet's atmosphere, making it inhospitable for life as we know it. Magnetic fields, invisible yet vital, shape our understanding of planetary environments. What is the heliosphere, and why is it important, you might ask? Well, imagine our solar system nestled inside a massive bubble. This bubble is the heliosphere, created by the sun as it spews out a steady stream of charged particles known as the solar wind. The heliosphere acts as our protective shield, blocking and deflecting most of the harmful cosmic radiation that hurtles through space. Without this protective bubble, life as we know it would be under constant threat from these high-energy particles. Scientists study the heliosphere using spacecraft like the Voyager and IBEX, which send back invaluable data about its size, shape, and behavior. This research helps us understand our place in the universe and how to better protect our planet. So, next time you look up at the night sky, remember this: our very own shield in space, the heliosphere, ensures our survival in the cosmic ocean. How do we unravel the life story of stars? Let's dive into the cosmic chronicles. Scientists use different techniques to decode the evolution of stars. One of the primary methods involves studying color and brightness. Stars, like humans, go through distinct life stages, and their color and brightness provide clues about their age. For instance, a star in its infancy is often surrounded by a nebula, a cloud of gas and dust, and glows bright and hot, giving off blue light. As it ages, the star becomes a giant, cools down, and starts emitting reddish light. The distance of a star also plays a critical role in its study. By measuring the distance, we can estimate the star's luminosity or intrinsic brightness. This helps us understand whether the star is at the beginning of its life, near its end, or somewhere in between. From the birth in a nebula to their final stages as a white dwarf, neutron star, or even a black hole, every stage of a star's life is fascinating. Every star has a story, and we're just beginning to understand them. What makes a planet just right for life? It all comes down to the habitable zone, or as it's often called, the Goldilocks Zone. This is the area around a star where a planet, if it's in the right spot, could have just the right conditions to support life as we know it. You see, being in the habitable zone means a planet is not too close to its star, where it would be so hot that any potential water would evaporate. But it's also not too far away, where it would be so cold that all water would freeze. It's in that sweet spot, just the right distance from its star, where a planet could potentially have liquid water, a key ingredient for life. The habitable zone is significant in our search for extraterrestrial life. It's where we focus our efforts, looking for planets that might have the right conditions for life. The search for life begins in the habitable zone, where conditions are just right. How have galaxies changed over billions of years? This is a question that's been on astronomers' minds for decades. To answer, they've turned to two main tools: deep space observations and computer simulations. Deep space observations involve looking at galaxies far away from us. Because light takes time to reach us, we're essentially looking at these galaxies as they were billions of years ago. It's like having a time machine that lets us see the universe's past. Computer simulations, on the other hand, allow us to predict the future. By feeding in what we know about the laws of physics and the properties of galaxies, we can simulate how they might evolve over billions of years. These two techniques, when combined, give us a fascinating glimpse into the life story of galaxies. We're learning that galaxies, like living beings, evolve over time. They're born, they grow, and they change. Galaxies, like living beings, evolve over time, and we're on a quest to understand their life history. Where does Earth end and space begin? Meet the Kármán line, an imaginary boundary drawn at an altitude of 100 kilometers, or roughly 62 miles, above Earth's sea level. Named after the Hungarian scientist Theodor von Kármán, this line marks the boundary between Earth's atmosphere and the infinite expanse of outer space. But why is it important? Well, the Kármán line holds significant sway in the realm of space law. It's the line that determines whether a flight can be classified as aeronautical or astronautical. It's the line that separates astronauts from pilots, and it's the line that distinguishes national airspace from the international expanse of outer space. It's more than just a theoretical boundary, it's a benchmark for human achievement and exploration. The Kármán line, a boundary both real and symbolic, separates us from the vastness of space.